Now, what I want to say here is there is an abstract way to view rational maps. Just maybe before we do this, just a word on terminology. I say rational map as opposed to rational function, right? So rational functions are these guys. They correspond to maps between E and the projective line. And a rational map is supposed to distinguish the case in which we talk about a map from E to itself, or even more generally, it could be from E to another elliptic curve E prime. And generally in mathematics, the reason we want to, I mean, even if we are only interested in an object E, we would like to understand all the self maps of E. And a rational map is a reasonable notion for a self map of an elliptic curve. If you want, one justification is that it induces this map for any, I mean, on all points. And there is an abstract way to view rational maps, which is as follows. So recall K bar E is a field. I remind you what it is. It's like you take all expressions of the form f over g, where f and g are polynomials over E, and G is not the zero polynomial. And here I write it slightly informally, because on these quotients we have an equivalence relation, just like with rational numbers. I mean, just like 1/2 is 2 quarters and so on. The same equivalence relation holds on rational functions. And this is a field. I mean, you have an additive inverse, and you have a multiplicative inverse for any non-zero element. I mean, the 0 and 1 are the constant rational functions. I mean, so this is like, so I claim that this is a field. So the zero element is simply 0 over some over any g, basically. 1 is simply 1 over 1, and the inverse, I mean the additive inverse of f over g is minus f over g, and the multiplicative inverse of f over g is g over f. Sorry. Okay, so this is a field. Now, this field contains a copy of K, because you can view elements in K as constant rational functions, right? It's like K by K bar E contains a copy of K, thought of as constant rational functions. That is K bar E and also KE. I mean, I do it for K bar because we need it for K bar, but it's true also for K of E. K bar of E extends K. This is a field extension, and this is maybe an interesting example that we didn't discuss so much until now. I mean, we saw that if K is FP, if K is FP, then we have this tower. In fact, it's like a partial tower. FP is contained in FP square, and it's also contained in FP cube. And both of these are contained in FP to 6, and so on. And at the top of this this chain, there is FP bar, which is like the union of everything. But a K of E, I mean, given an elliptic curve, K of E does not belong to any part of this chain. I mean, K of E is another way to extend FP, which is not part of this chain. And we didn't discuss the general construction of algebraic closure, but you could also do algebraic closure for the field K of E, and it will result in another chain, and K of E bar is at the top of this chain. So you see, I mean, there are in fact many other fields that can extend FP, and the algebraic closure is not the last word in field extensions. But for us, what is interesting, you know what? Okay, so what is interesting is the following. We can consider E over K of E, right? Because the equation of E has coefficients in K, and a K of E is an extension of K, is a field extension. So I can consider the set of solutions for the equation of E, but in K of E. Then I can consider the K irrational points. Let's put K bar here, because we usually consider the rational functions over the algebraic closure. And what are the points E of K bar of E? These are pairs R comma S, such that R and S are rational functions on E, and they satisfy the equation of E. But when you consider the equation of E, over the new field of rational functions over it. That is s square equals r cube plus ar plus b, and here a and b are considered as a constant rational functions. And we have the point at infinity, which I want to distinguish it from the usual point at infinity, so I will write O of m. So the finite points are simply the rational maps. Is this clear? This is a bit abstract, but soon you will see why it is useful. Or let me say immediately why it is useful. This means that for f and g rational maps, we have f plus g, which is the addition in this elliptic curve. Okay, I mean, let me write it like this. F and g are simply elements in the curve E defined over the field of rational functions, and hence I have f plus g that is plus in the elliptic curve. So f plus g is another point on the elliptic curve, which is a rational function. I mean, since f and g are finite points, f plus g is, well, I mean, it could be that f is equal to minus g or something like that, and then they become the element O of m. By convention, O of m, the constant, map on O is considered a rational function, a rational map. Yes.
Hi, one question. So here you say that the plus of f plus g, this is like you said over the elliptic curve, but they are not points, right? They are rational functions over the elliptic curve, or is equivalent to being points?
So they are points in the elliptic curve considered over the field of I mean the field ke or k bar e.
So it's just like to try to wrap my mind around it. So in the real world, this would be just like points.
It would be no. Each of f and g is like a pair of functions, a pair of rational functions, s, r, and s, right? But these pairs, this pair of rational functions can be thought of as a pair of coordinates of a point in E, but over a different field, over the field of rational functions.
Okay.
Okay, it's a bit abstract, but this kind of view is very useful, because then I can immediately see that I can add them. I can add the two rational functions. I mean, then what you should consider, I mean, there is a naive way to add two rational functions. I mean, if I give you r comma s and t comma v, so naively, you could say, I mean, I could definitely add two rational functions. So I could define this to be r plus t, s plus v. But this is not a good definition, because there is no reason to expect that now s plus v squared would be equal to r plus t cubed plus a r plus t plus b.
Okay.
Right?
Yeah. Okay. So you constrain it to the.
So I need to do a different. I need to do a different addition. I mean, the naive addition doesn't work. So how do I find the appropriate addition that gives me, for a pair of rational maps, gives me a canonical a third map? I view the rational maps as elements in an elliptic curve of, in this elliptic curve. I mean, it's basically, it's the original equation of the elliptic curve, but interpreted over a field extension of K. This you can always do, right? I mean,
Yeah. Thanks. Yes.
okay. So, and once I view f and g as elements in this new curve, then I know what is the addition. And this is, and I can write the formulas, but I will avoid it for now. Yes, Lisa.
I'm not sure I understand why we jump between a set of finite points and set of finite points plus this 0m.
Well, I mean, finite points is here. It's like, because a rational function, a rational map, as I defined it last week, is always a pair of functions R and S.
Right.
So it is really the finite points, as I defined it last week. It's really the finite points of this curve, right? Finite points simply mean not the point at infinity.
Yeah, yeah.
Okay.
I mean, why we should consider point at infinity as well? Why we want to consider?
Well, I mean, this is a curve. This is a curve. So I mean, if you want to consider it properly, you need, if you want to have, the abelian group structure, you need the zero element.
Oh, I see.
Okay, but I denote the zero element here differently than the zero element in E of K, right?
Yes.
E of K also has a zero element, which we typically denote as O.
Yeah.
And now I want to disambiguate the notation, so I call the zero element here in the orange box O of M.
Mm-hmm.
And now I say, okay, I mean, since rational maps, as we defined it last week, are the finite points of this orange curve, let me extend the definition and say that O of M is, I also call it rational map, because it's convenient for talking about this, right?
Mhm.
Okay, and the a 0M, you can think of it as the map from E to E that sends everything to 0. P is going to 0. I mean, okay.
Okay.
So this is also, I mean, whether we call it a rational map or not, it's by convention, but you will see that it's convenient to consider it as a rational map.
Okay. Makes sense.
Okay, so now we have an issue to resolve, and that is the following theorem. Sorry, before I move on, Nicholas, are you following?
Yes.
Okay. So the following theory may look trivial, but it's in fact not so trivial. Let E over K be an elliptic curve with K algebraically closed. And then for rational maps, F and G, and K being the result of the elliptic curve addition of F and G. We have K of P is equal to F of P plus G of P. For any P in E of K. Okay, so this may seem trivial, but it's not, because a priori the operation that I do here is happening in a different elliptic curve, right? It's in the operation here class is in the elliptic curve E of K of E. And the operation here happens in E of K. So, so when I do K of P, I first do the operation in E of K of E, and then I evaluate what I got. I mean, I get some rational function, and I evaluate the rational function I get at P. And more concretely, maybe before the proof. Okay, let's say note that even if F is not equal to minus G, to minus G or to G, or to the zero rational map, it may be that for a specific point P, f f of P is equal to say minus G of P. Okay, so you know, in this case, if f of P is equal to minus G of P, for example, then when you add them two together, you get O. But K is not the zero rational map. K is not O of M, because if F is not identically equal to minus G as a rational map, then K would not be equal to the zero rational map. You see? So a priori, we would need to kind of make sure that even in this case, K of P, I mean, K would not be the zero rational map, but K of P would still be zero. So you see, this is the kind of tension that we need to resolve. Is this point clear? I mean, I think that's maybe, I mean, to really see why we need to prove this is a big portion of the proof. And now, are you following?
Yes, sorry.
Okay, so it's important. I mean, this kind of stuff that may look very easy at the beginning, they turn out to be quite involved once you really try to pin down the details. Okay, so let us write recall the addition on E of K of E. Yes. I don't get the remark. Can you say it, Lisa?
It's not important. It's not important. Just you tell that like it might look like trivial or something, and I just thought that it looks as trivial as like thinking that like if oh, I wrote it in the wrong way, but like never mind. It doesn't matter. It doesn't matter.
Yeah, I mean, really, the point is that we have different additions here. It's like one is the addition in E of K of E, and one is the addition in E of K. I mean, first, and in what happens in this this equation double star is that we, on the left side, we first do the addition in E of K of E, and then evaluate at P. And in the right hand side, we first evaluate both functions at P, and then we do the addition in E of K. And it's not clear a priori that these two things coincide. Of course, we would like them to coincide because it will make our life much easier. Okay, so how does addition look like in E of K of E? I mean, I'm going to write the formulas that we discussed before. I'm not going to develop the formulas again. So say F is R comma S, G is T comma V, and K, which is F plus G, is W comma Z. Okay, all the small letters here are irrational functions on E, and the formulas are W is minus T plus R plus lambda square, and Z is minus V minus lambda W minus T, where the lambda, it has two cases. If R is different than T, again, different than T in the rational function, in the field of rational functions. So if R is different than T, then lambda is given by S minus V divided by R minus T. And if R is equal to T, then lambda is 3R squared plus A divided by 2S. Okay, what these formulas do, they do exactly the same thing as if you would have, I mean, this R, S, T, and V, if they would be elements in K instead of functions, you would have the same formulas, right? It's like that's the way to define addition on an elliptic curve. Okay, so suppose first that R is different than T. This means that let me call it say 1 and 2. So we are case 1. So in case 1, we use lambda as in equation 1, and still there are things to verify. So okay, if R and P, R of P, and T of P are finite and not equal, then we are okay, because then it means that when you do the addition of f of p and g of p, you will use the same type of lambda, right? I mean, if you want, the whole complexity follows from the fact that R of, R and T may be different rational functions, but they may be equal at a certain point P. If they are equal at a certain point P, then we need to check something, because the way, I mean, we always have W and Z given by these formulas, but if R is not equal to T, then the lambda is as in equation 1. And then when I do the f of P and G of P, if R of P happens to be equal to T of P, then I will use a different kind of lambda. I will use a lambda equal to this guy, where you substitute P everywhere. So I would need to check that these two things are equal. But if R of P and T of P are both finite and they are not equal, if they are not equal and finite, then I use for the formula of f of P and plus G of P, I use this lambda. This lambda when you substitute P, so everything works. If R of P and T of P are finite and equal, then either, I mean, if you have the same x coordinate, R and P and T are the x coordinates, right? So if you have the same x coordinate, the y coordinate can only differ by a sign. So this means that S of P is equal to V of P, or S of P is equal to minus V of P. Right? That's the only two options if you want the point to be on the curve. So let's do a case 1. Okay, so if S of P is equal to minus V of P, then clearly F of P is simply the additive inverse of G of P. So when I do F of P plus G of P, I get the point at infinity. So this is the right hand side of the equation we always need to check. And on the other hand, remember, we are in case 1. Case 1 means that R is not equal to T. If R is not equal to T, then I use lambda as in equation 1. And we see that this lambda will have a pole at P. Lambda equals S minus V R minus T. will have a pole at P. So everything is fine, right? I mean, so K of P, I mean, I only need to calculate the x coordinate of K of P to know that it's, I mean, if the x coordinate is infinity, then K of P must be infinity. Remember, if we have this a pair of rational functions R and S that become together a rational map, then they have exactly the same poles. I mean, one is infinity if and only if the other one is infinity. This is kind of the the condition of being a rational map. Okay, so this is if S of P is equal to minus V of P. I guess the second case is a bit involved. So if R of P, T of P are finite, and I mean we're in the case that they're equal, and S of P is actually equal to V of P. So the formulas for f of P plus G of P and for K of P, they only differ possibly by the definition of lambda. So since S is not equal to minus V, we have, I can write lambda as follows. I write lambda as V minus S divided by T minus R. This is, I think I wrote above S minus V divided by R minus T, but this is the same. And now I multiply and divide this by V plus S. And I can do this because S is not equal to minus V. So I'm not dividing by the zero rational function. Okay, but then I open it up, and this is T cube minus R cube plus A T minus R divided by T minus R V plus S. And I can further rewrite it as a T square plus RT plus R square plus A divided by S plus B. Right? This T t cube minus r cube, I can divide it. I mean, I can cancel t minus r from it. And this is what I'm left with. If S of p, which is equal to V of p, is non-zero, not not the element 0 in K, then I can evaluate everything at P. I can this becomes you check it out. I mean, T so R of P is T of P. So I have 3r squared plus A divided by 2sp. Okay, and so the lambda, so this is the lambda of K of P, right? So K of P is actually equal to F of P plus G of P. Right? I mean, the only thing I need to check in this equation is that the two lambdas are equal. So if R is equal to T, sorry, if R of P is equal to T of P, then the lambda I use is the second lambda, right? This lambda. So I need to check this is the lambda I use for F of P plus G of P, and I need to check that the lambda I use for K of P, which is this one, number one, because R and T are assumed to be different rational functions. I need to check that when I evaluate this lambda at P, this is the lambda of K. When I evaluate it in P, I actually get this guy evaluated at P. Is this clear? I know it may be a bit hard to do the bookkeeping.
Maybe can you repeat the second case of B?
Yeah. So the second case is the case in which S of P is equal to V of P, right? Because I mean, if R of P is equal to T of P, it means that F of P and G of P have the same X coordinate.
Right.
And if 2 points on the curve have the same X coordinate, the Y coordinate can be either equal or the opposite sign. Right. So this is the reason that that we have only these two cases, 1 and 2.
Mm-hmm.
Okay. So I assume that the Y coordinate of F of P and G of P is equal. But of course, the rational functions S and minus V are not equal. So otherwise, if they would be equal, the claim would be trivial.
Right.
I mean, right? Because if the rational functions S is equal to minus V, and are, then f itself is minus g. You see?
Yes.
Okay, so I assume s is not equal to minus v, and then I take the lambda of k, and I multiply and divide by v plus s. I get these equations that can be reduced into the last one, this last fraction.
Mhm.
Now I substitute. I want to calculate k of p. In fact, I don't really need to calculate all of k of p. All I need to know is that the lambda of k, that when you substitute it in, when you substitute p in it, is equal to the lambda that you use when you do f of p plus g of p.
Okay.
Okay? What is the lambda that, when I do f of p plus g of p, what is the lambda I use? In our case, we assume that s of p is equal to v of p. And sorry, we assume that r of p is equal to t of p. So the lambda we use is this 3. The lambda we use is this 3r squared plus a divided by 2s when you substitute p in it.
Mhm.
Okay, so I need to check that this lambda, the first lambda. So I take the lambda of k and I substitute a p in it, but I got this expression, right? I got this blue expression, and now I substitute p in it. Let's suppose that s of p, which is assumed to be v of p, is not 0. Then I can substitute a p in the blue box, and what I get is 3rp squared, because everything on the in the numerator, everything beside the constant is equal to r, right? You have like t is equal to r.
Mhm.
So I get
Oh, I see.
yeah, I get 3r of p squared plus a divided by 2sp. So I get what I want.
Yes. Yes, I see.
Okay.
I missed this step before.
Yeah. So this is like what we need to do here is to compare the lambdas. The rest has to be the same, but the lambdas may cause some problem. Okay. Now, finally, if s of p, which we assume to be equal to v of p, is equal to 0, then f of p is a point of order 2. Both f of p and g of p. Right? The only points on the curve that have a 0 y coordinate are the points of order 2. And if f of p is a point of order 2, then lambda, I mean, this lambda, I should write, I guess, lambda of k evaluated at p has a pole, or a p, let's say p is a pole of a lambda k. Lambda k is like this s minus v divided by r minus t, which is equal to the blue box. Right? So but in fact that's what we want. I mean, it has a pole. If it has a pole, it means that k at p is equal to O. And then since g of p is also of order 2, f of p plus g of p has to be equal to O. If you add 2 points of order 2, you get O. I mean, sorry, f of p is equal to g of p. So if you add a point of order 2 to itself, you get O. And so we see that also in this case, k of p is equal to f of p plus g of p. Okay, so we covered the two cases of B. So we covered A. If R of P and T of P are finite and not equal, then this is by definition. B, if they are finite and equal. And now we need to deal with some other cases, but I suggest that we take a break here and we continue in 10 minutes. Of course, unless you have any question. David, I see that you just joined us. Okay, so let's meet in 10 minutes. Okay, so we continue with the cases. The next case so we do the case in which exactly one of f of p and g of p say f of p is the zero element. Recall that f is r comma s. So by assumption, s and r have poles at p. Now, if rational functions have poles at p, whatever p is, I can take uniformizer at p and write r is equal to r1 divided by u to the d, and s is equal to s1 divided by u to the e, where u is a uniformizer at p. Right, and d and e are the multiplicities of the pole p. Now remember that r comma s is a rational function. That means a rational map. It means that it satisfies the equation of the elliptic curve, and I can substitute instead of r and s these things, r1 divided by u to the d and so on, and what I get is that s1 square is equal to u to the 2e divided by u to the 3d times r1 cube plus a u to the 2e divided by u to the d times r1 plus u to the 2e times b. I mean, what I did here is s1 square is simply, sorry, s square is simply s1 square divided by u to the 2e, and I multiplied all the equation by u to the 2e. Okay? Now, this means that 2e has to be equal to 3d, because s1 is finite, right? I mean, s1 is finite and non-zero. U is 0 at p, so if a 2e is not equal to 3d, then either this expression, when you substitute p, either it becomes a 0. If 2e is bigger than 3d, then it becomes 0, and everything else on this right hand side becomes 0. Or if 2e is smaller than 3d, then this expression becomes infinity, but S1 is not 0 and not infinity at p. So the only option is that 2e is equal to 3d. And furthermore, I must have, so now that I know that 2e is equal to 3d, I also know that S1 square evaluated at p has to be equal to R1 cube evaluated at p. Right? Because when I evaluate at p this equation, triangle, everything else vanishes. I mean, when because 2e is bigger than d, then this guy, when I substitute p, it's like u to the positive power at p. This is 0, and this is also 0. And so this thing cancels out, u to the 2e divided by u to the 3d, and I get this the second condition, S1 squared at p equals to R1 cube at p. Is this clear? Lisa, Nicholas?
Somewhat.
So tell me what is not. I mean, maybe one thing that I forgot to say, I mean, when I wrote here in the orange box, this is a uniformizer business. It means that if I have a pole, if let's say R has a pole at P, then I can write R as R1 divided by a uniformizer to the D, where R1 is not 0 and not infinity at P. This you remember?
Yeah.
Okay, this is like this uniformizer stuff. I mean, we proved that uniformizers exist for all points.
Yep.
And so now I have the equation s square equals to r cube plus ar plus b, right? And I substitute in this equation, I substitute r1 divided by u to the d instead of r, and the same for s. I substitute, and I mean, so s square, for example, would be s1 square divided by u to the 2d, right? This guy would be s1 square divided by ud squared. It's u to the 2d.
Yep.
Okay, and so I multiply all the equation by u to the 2d, and I get this equation triangle.
Okay. Yeah.
Okay, this is an equation of rational functions, so it has to be true for any point that you substitute. Now, S1 at P is not 0 and not infinity, right? This is by, again, this uniformizer business. I mean, I can always write a function that has a pole at P by a function that it does not vanish and does not have a pole at P, S1, divided by this some power of the uniformizer. So S1 at P is not 0 and not infinity. But if 2 of E is different than 3 of D, then U to the 2 of E divided by U to the 3D is either 0 or infinity, right? Because U to the U at P, when you evaluate U at P, this is another property of the uniformizer. U at P is always 0.
Yep.
Okay, so I get that a 2E has to be equal to 3D. But if 2E is equal to 3D, that means that 2E is bigger than D.
Yeah.
Which means that when I substitute P in this expression, this blue guy, I get 0. Because U of P, or U to the positive power at P, is 0. So it means that this guy becomes 1, this guy becomes 0, and this guy also becomes 0. You see, Nicholas?
Yeah. Yeah, I think I see now.
Okay, and now, so then I get that S1 square evaluated at P has to be equal to R1 square evaluated at P. Okay, and now we run a computation. I mean, it's just a manipulation of symbols. Let's do a W. I want to calculate W. Remember, K is W comma Z. And I want to, I mean, I know how to calculate F of P and G of P. And now I want to calculate a K of P. So in order to calculate K of P, I need to calculate what is W and what is Z. So W is minus T plus R plus lambda squared. But lambda, in our case, we are in the case that R is different than T. So lambda is S minus V divided by R minus T squared. Okay, so I write it down. I mean, it's in the notes. You can manipulate the symbols, and you get T R squared plus T squared plus A R plus V squared minus T cubed plus B minus 2VS. And all of this is divided by R squared minus 2TR plus T squared. Okay, and now remember, I have this. I mean, R is R1 divided by U to the D, and S is S1 divided by U to the E. So I can plug it in the last fraction that I got, and what I get is T R1 square times u to the minus 2d plus t squared plus a r1 u to the minus d plus v squared minus t cube plus b minus 2v s1 u to the minus e. And in the bottom, I get r1 square times u to the minus 2d minus 3 tr1 u to the minus d plus t squared. Okay, I mean, I hope you can believe me that this calculation is okay. And now I simply write it a bit more clean as tr1 square plus ud r1 minus 2v u to the 2d minus e s1 plus u to the 2d at plus 2b and then divided by r1 square plus u to the d r2 plus u to the 2d t squared, where r1 and r2 are finite at p. And now I evaluate the whole thing at p. When I evaluate the whole thing at p, many things vanish because u with the positive power evaluated at p is 0. So w evaluated at p, this whole fraction is supposed to be w. W evaluated at p is let's see what vanishes. This vanishes, this also vanishes, and this also vanishes. So I get t evaluated at p times r1 square evaluated at p. And in the bottom, this vanishes and this vanishes. So I get r square, sorry, r1 square evaluated at p. And then these things cancel out. So I get that w of p is t of p. But that's exactly what we want, right? Because remember, we are in the case in which f of p is equal to O. And that means that f of p plus g of p is equal to g of p. And the x coordinate of g of p is t of p. So we get that the x coordinate of k of p is the same as the x coordinate of g of p, and that's part of what we want. And similarly, one can show that the y coordinate of k of p equals that of g of p. And as a result, k of p is equal to f of p plus g of p. Okay, so this is our case, and we are almost done. I mean, now it's going to be the easy part. So D, suppose both f of p and g of p are the point at infinity, O. Of course, I could do this calculate, like a similar calculation to what I did here in the previous case, but that's a very long way, and I have a shortcut, and the shortcut is to use we use the associativity in E of K of E to deduce I mean, I know that K is equal to F of F plus G, and this means that F plus G minus K is equal to the zero element in the elliptic curve E of K of E. And in fact, by associativity, I can do F plus G minus K is equal to O of M. Now, denote K of P is equal to Q. If Q is equal to O, we are done. Because then clearly, I mean, our assumption is that both f of p and g of p are O, and if k of p is O, we did what, I mean, we proved what we have, what we wanted, and otherwise, otherwise, minus k of p is equal to minus q, which is not O. Hence, by the previous case, case C, I mean, if I have two rational functions and I want to evaluate them at a point, and exactly one of them is zero, then I can evaluate the sum of the rational functions at the point. this is case C. So I get that G minus K at P is equal to G of P minus K of P, which is equal to minus Q, right? I mean, it's equal, G of P is equal to O, K of P is equal to Q, so I get 0 minus Q, this is minus Q. But I also know that also by KC, now I know that G minus K evaluated at the point is non-zero, it's minus Q, and F evaluated at the point is zero, F of P is zero. So I use KC again, and I get that F plus G minus K at P is equal to F of P plus G minus K of P, which is 0 minus Q. And this contradicts, this has to be equal to 0m evaluated at P, 0m evaluated at P is 0. That's a contradiction. Okay, so you see, this is a shortcut using this associativity on this higher level. I get that. So we must have that K of P is equal to F of P. And we must have a Q is equal to O. Hence, K of P, which is Q, is equal to F of P plus G. Okay, so we are almost done. Now, okay. And so case 2 is that R is actually equal to T. If S is equal to minus V, then F is equal to minus G as a rational map. Hence, K, which is F plus G, is equal to the 0 rational map. And this is indeed compatible. I mean, so K of P is O, and clearly F of P plus G of P is also O. So we are okay. And the last possibility is that S is not equal to minus V. So assume S is not equal to minus P. But of course, S of P may still be equal to minus V of P. Now, since S is not equal to minus V, it means that F is not equal to minus G as a rational map. But remember, we are in the case where R is equal to T. So F and G have the same X coordinate. If they have the same X coordinate and they don't have the same Y coordinate, sorry, if they have the same X coordinate and they are not a additive inverse of each other, then they must be equal. And since R is equal to T, F is equal to G. So now we have two possibilities. If R of P is finite, then K of P is equal to F of P plus G of P, because they are identically defined. If R of P is equal to O, then we have something to check. But remember, F of P and G of P, I mean, F is equal to G. So F of P plus G of P is simply the formula for doubling a point. In this case, F of P. The duplication formula is W is the X coordinate of K, is minus 4RS plus 3R squared plus A divided by 2S. But if R of P is O, this implies automatically that S of P is O, because we're talking about a rational map R comma S, and this formula shows that W has a pole at O, at P, which means that K of P is I mean, if the X coordinate of K of P is infinity, then so is the Y coordinate, and so K of P is equal to O. And this, let me just check. Yeah, so this should complete the proof, but I'm missing something. So yeah. So if R has a pole at P, yeah, if R of P is infinity, then S of P is infinity, and this means that F of P is infinity. I mean, the point at infinity, which is equal to G of P. So, and indeed, in this case, K of P is also the point at infinity. So it is, it checks out. Okay, so this is this completes the proof basically. This covers all the cases that show that you can do a pointwise addition. This theorem in orange. You can do pointwise addition of rational functions. Any questions? I know it's been a long one.
I'm not quite sure I understand when we were going through case C, and we were making some transformations in the equation. We like there is a large R that popped up from nowhere and then disappeared again. I didn't understand
Yeah,
what it was.
I just wanted the. I mean, it's not crucial. You can even do the same. I mean, I just wanted to write it so you see you have TR1 square. I multiplied all the equation by u to the. I mean, all the fraction by u to the 2d. Right. So then I get I mean, in the second expression, the blue one here, I had something times u to the minus d multiplied by u to the 2d is something. I mean, u to the d times something. This R1 is this something. R1 is t squared plus a times small r1. Okay, R1 is t squared plus a.
Oh, I see.
Small r1. And the
So
same
just confusing because R was large, and before that we used large letters for other notations.
But not for the R and S.
Yeah, sure.
Okay, but I'm sorry for that. But that's just to simplify. It was just to simplify the equation.
I got it.
The whole point is like it's u to the d times something that does not vanish at p. That I mean that is finite and does not vanish at p. Okay, so this is and the same for R2. So when I multiply it by actually it could vanish, but it's finite. So when I multiply it by u to the d and I evaluate it at p, I get 0. Okay, now well, I guess that's a good place to stop. Unless now maybe you have another question, Nicolas.
No questions from my side.
Could you follow or now?
So yes, but my feeling is that I need to do like a second round by myself because, like, I mean, it was very I mean, it's a lot of steps and a lot of things to be kind of unfolding along many pages. So yeah, I guess this weekend I will go over it again.
Yeah. Okay, no problem.
But I mean, the general idea, yes, it's just that I would like to go like in deep for each step to make sure that I fully follow.
Yeah, let me just say what I will do next time, but it's a corollary of this. I mean, we want to show that the map n from E to E. I mean, I said that it's a rational map, but I didn't prove it, right? I mean, this it takes a point P and send it to NP, right? And I want to say that this is a rational map. So how will I do it? I will decompose n as n minus 1 plus 1, and I will prove by induction. I mean, but I need to know that when I evaluate this at P, I can do. I mean, when I evaluate the right hand side at P, I can separate the terms. Right. So this would be one application of the theorem. This is because of the theorem. Okay, and once I know the theorem, I can use this equality to prove by induction that multiplication by n is a rational map. And it has consequences. I mean, if multiplication by n is a rational map, remember, we showed that a rational map is either constant or surjective. Okay, so all things are aiming towards understanding points on elliptic curves, but they sometimes they go a bit wild. All right, that's it. So I'll see you next week.
Thank you very much. Have a nice weekend. Bye.